Okay, so what were we talking about last time? Folks remember?
uh, or actual
We're attempting to get back on track, but we're very much behind where it's supposed to be. Um, Technically, we are in week 3, lecture 2 in the slides, but this is like week 5, I think, or something like that. It doesn't help that the very first class was a holiday, and then we just had a holiday last week, so we only got one class. So we're trying to catch up. But apparently the way that I laid it out is not always going to be the same. So I've been moving some stuff around. But if you are up to 4.2 in the book, you're good. Okay. This is where I think we were, and correct me if I'm wrong. God, it's possible to see anything. So what is the statement? Say that again. The change of mass is what?
Must equal zero for its reference. For the change, must equal zero.
Okay, good, good. That's a great way of sort of conceptualizing it. So can someone other than Elliot tell me what we mean by what do we mean by the change? Start with the given mass. They can't have more mass of this atom. Right, but there is a way to get more mass into a system, right? Open. Yeah, open system. So we have some control parcel, some jelly bean. What's the way to get mass in? Putting stuff in it, going through the control volume is the only way to make the time period, right? Do you recall that? So you might say this. Wait, what the fuck happened to my? Where's my chalk? Shit. Are you serious? Thank you. Okay, so we have a statement, a physical statement that we can use here. What's the math look like? Anyone can answer this one. What do we mean by D there? How big is the D?
Small thing.
Small D?
Small.
Like this?
Lowercase. Lowercase.
No. You're right. That is one that we do use, but we have a simplified version. We're gonna.
But it's your TV, but it's your bank.
This is not an integral formalism. Yeah.
So it would be the derivative of the density of the volume, of that volume. It's like the heat.
Uh-huh. But you're saying volume, and I just said that we're not using the integral formalism.
Gotcha.
We use the integral formalism in order to present it, right? That's the idea that you have this jelly bean, the stuff goes in. But the equation that Elliot was talking about at the beginning is the one that allows us to connect that integral formalism to derivatives. The derivatives are rates of change, and the integral formalism allows us to see things passing through surfaces because we can integrate over those surfaces of volume. So in fact, the form we're going to use here is just slightly easier to write. It's the partial with respect to t of rho plus the partial with respect to x. And what I'm going to do here is I'm going to use the index notation of rho, well, backwards rho ui. And what's that equal to? That is equal to 0. Good. So now, and I told you that we're going to start doing this at the beginning of every class. This is where we introduce the terms, and then we have to define them in words. So what's the first term?
That's you.
Good. And what's the name of it? Correct. That is a steady or unsteady term. What's this term? Correct. That's the vector term. Good. Okay, so what do they both mean? Either one is fine. What do you mean by the change in the control?
This is
Okay, yeah, so there's some words that I want to highlight there, right? Entered is important. We're talking about changes here. We're going to want to be able to describe these in as simple as terms as we can. So like how you explain this to your cousin. What do each of those two terms mean?
what you started with and what you had.
What you started with,
What you
what
had.
you added into it. Okay, I like about 75% of that. Because this, unfortunately, what you started with, right? Like, this is changes to the server. So it's almost exactly there. And then what you added can also be modified because it's also what you exactly, right? And that's maybe a negative plus, right? That's okay, the okay way to say it. And if I were to explain this to my cousin, I'd say we changed the room's composition by adding people. Right? That's a perfectly fine way to say it. And that's an oversimplification, right? That's okay to have that oversimplification because we need to understand this component of a term like the steady or the advective thing when we're talking about mass density, because we're about to talk about much more abstract things. So you have a very good sense for how the mass would increase at a person, right? We are now going to talk about how momentum in a fluid is transferred. And that you will have a lot worse, what's it called? Not like gut feeling, but intuition for, right? It's just not something that we really think about on a day-to-day. Okay. Okay, so we talked about the incompressible flow. Let's take a detour into what we call a stream function. This is a special example. What did we call an incompressible flow, by the way? What does that mean? Yeah, density doesn't change with pressure. I would even modify that slightly. I'd say when the density doesn't change. And in particular, if you have this condition, del dot what equals 0. Del dot U. Okay. That is an incompressible flow. Notice how this doesn't say anything about the density? Right? So it's not about the material properties that make it incompressible. It is certainly the case that some fluids are incompressible, but you can also set up the velocity field such that it was an incompressible flow. Do we see how that's possible? Because these are gradients in x dotted into the x components, right? So if, for example, your derivatives of the the x derivatives of the velocity in the x direction don't change, then you would get 0, right? And so on and so forth with the rest of the dimensions. And we'll see examples of that. Okay, so we had that continuity equation, the conservation of mass equation. If I say, let's use the unsteady version of the equation, you would use both terms. And if I said, let's use the steady version of the continuity equation, how would I write that?
Just the first term. Equal to.
First term equal to 0, right? So all I would have to write was the second term. So then I could write something like this. Del dotted rho U. Right? And the cool thing about that is that we can create a vector potential. What does that mean? Why would you care? Let's do it. So I can make this a bold statement. I can say something like rho U is equal to del cross psi. And this here, that is my stream function. Now, it's a mathematical construct. Okay, you can't touch a stream function. But this has the really fun property that if I put this thing in here, see what happens. Oops. Del dot del cross. What's that?
Disable. Honestly, I think that's wrong. So they do that.
The divergence of the curl. Yeah. That would be correct. So this is taking advantage of a beautiful little vector calculus relationship, which says that the divergence of the curl can't then be dotted into the curl. Let's have a look at why that is. Here's your divergence. Here's your function, right? The divergence across the function is over in that direction. They are orthogonal to one another. Let's dot it back into the divergence. They're orthogonal to each other. So therefore, they're always going to be 0, right? You see that? So we can take advantage of that in order to create this thing that we call psi, and that allows us to describe the flow in terms of one scalar function. Okay. You could also write it as the vector one, psi, you can say is equal to, this is like a big psi of psi. Those all look like the same letter, but they're not. I'm sorry. So this is like psi, and then this is a different version of psi. So this would be here, the vector is on the left of the vector potential, and this here is the scalar. Okay. Yeah. So that's fun, right? there must be a vector potential for the flow whose result is the gradient of another scalar function. In practice, it's easier to do. You will see flows, or you will be given the stream function, and from which you can just do a couple derivatives, do a cross product, and you get the flow direction. Slides. What? You want to do an example here? Let's let's consider two-dimensional flow. Okay, we're gonna do x, y, just to make it simple. And remember that simple doesn't mean easy. But when I say the word simple, I mean that it's straightforward, not that you should be able to do it already. Okay, so let's have x and y. If you want in your notes, you know, you're welcome to make that x1 and x2. Those are equivalent. Okay. So let's ask the question, what happens when the streamlines lie in Z? What's the streamline again?
Instantaneous velocity.
Instantaneous velocity, okay. So let's imagine the streamlines lie in Z in constant planes. So Z is coming out of the board. And the velocity is tangent. The velocity is coming out of the board in constant planes. Does that make sense so far?
Would be like points then in that plane? Like lines?
Yeah, well, so if you know, if we're thinking about it like this, so we'll make a streamline. Let's say we have some flow like this, and we usually connect that with a nice beautiful line. But you might have a sheet, and that sheet might do this, and it has the same velocity, or you know, maybe the velocity is changing as it goes. But that is a whole sheet of flow moving in the same way. That can be described with a series of streamlines all along the sheet. And so in this particular circumstance, imagine, if you will, a sheet is coming out at you, maybe multiple. And they might have different values as well, but they're all paired. Okay, in this situation, Z is one of the three-dimensional stream functions, okay? So if we go back here, we see that this thing can be minus Z, so that you get X, Y, and Z in the right direction. Be able to see it like that. Okay. So why am I saying that? So I'm going to start with this here, this X. I'm going to call it minus Z. And why is that? Because when I do del of X, what do I get? What about the first derivative that is dx? This thing. What is the derivative of x of this thing? 0. Right? So dx of this thing in the x component, x hat. Well, that's 0. And why? Yeah, 0 is 2, right? The only thing that has a component here is z. Okay, and then the third one is edz of x z in the z hat direction, which is -1. So it's going to be minus z hat. Right? Okay, so what's rho u? Well, rho u, I guess, has to be minus EZ, or we can call that. Yeah, I'll try to be consistent here. Crossed with del psi. Well, this is okay, because think about it this way, right? This is the direction out of the board. Which means that this thing here, del psi, it's got to be completely in the board. Right? Because any direction that's out of the board, that cross is going to go to 0, right? So in fact, this gives us two equations. This immediately leads to, I don't know how to draw this better. Rho u and rho v. And I'm, hang with me because u is going to be our ux and v is going to be our uy. There's no w. Okay. So what do we want to write here? Well, I can do the derivative and I can see which components match up in the cross product. And it's kind of straightforward. It's just del y of psi. And that kind of makes sense, right? Because the z component here grabs the y component in the x-hat direction. And similarly, here, I grab a minus sign along the way, but it's the x component. So the y component of the cross product, right, has to have the y direction. And so therefore, in order to select the y direction from z, you have to use the x derivative. And because of the way that they're permutated, you get an extra negative sign. Get that yet? You guys see how that's worked out? Draw a cross product box. Del cross psi. What goes at the top? Good. Which ones? X hat. I mean y hat and then the end. Good. And then next. Partial what? Partial x. Partial y. Partial z. Good. And then next. X. 0. I'm going to use psi x. Psi y. Because we just want to keep this for later. We're going to use that a bunch, right? So if I'm selecting this guy, which is this one right here, then I just look in this box. And the first one here, del x of y, right? Minus del y of x. All right. And each one of those are going to have a correction. The u and the x. Right? U and the u. You'll understand that better when you use it. Okay. So that gives you your velocity. As long as you have sign. We can do the same in other dimensionalities, like for example, you can have a rotating cylinder or you have flow through a tube. You can use stream functions for it as well. I think it may make more sense to try. So maybe we'll put one of those on the market suite. And really a lot of what you're doing here at this section of the class is you're brushing up on your vector algebra or your vector notations. And you're getting really used to the ideas of curls and the ideas of derivatives, taking lots of derivatives. Okay. There shouldn't be a lot of intervals. Okay, questions, comments, concerns before we move on?
Yeah, you said the bottom equation, PU is a negative partials. Bottom. You said
Oh, yeah.
that's in the y direction.
PV.
Oh, PV.
Yeah, this is V. So this is the V component. So that would mean this is in the Y direction. I can make that better. I can do this, right? That would probably be easier to show. Because this, of course, is a vector. But what I did here is I just got rid of that symbol. And if I get rid of this symbol, then it's the scalar quantity. Okay. Are you ready for the meat? All right. How do we get momentum? What is momentum, by the way? Right. Yeah. So that's this weird product, m times v. What does it mean? Okay, interesting. There is a very natural relationship between something that keeps something moving, which is called inertia, and momentum. But in fact, they're not exactly. So the correlation there has everything to do with mass. So the mass is what keeps something in motion if it's in motion. Objects that don't have mass or have less mass can be more easily deflected, right? Can be changed in their motion. Their natural resistance to change in motion is smaller than objects with more of that thing, which we call mass. Momentum is a weird combination thing that combines your natural resistance to motion with motion. So is it better to be run over by a 2-year-old child or a 250-pound linebacker? The child. Wow. Less mass, right? Probably moving more slowly, right? Is it better to have a bullet shot at you or a child thrown at you? A child, because the child is more massive, but moving much less quickly, right? So it's this combination of these two. Okay, and this is where fluid starts to get hard fast. Because we have for a lot of our life dealt with linear phenomena. What I mean by that is if I were to take this and I were to toss this to Kevin, he'd be able to calculate, basically his brain is already doing that calculation. It's going to go up in a parabola and it's going to come right back down, right? So he knows where to put his hand out, not just from experience, but also from like doing a calculation. You know how fast it's going to be, how to pull your hand back, right? All of those things become innate. That's because the equations of motions are linked. X equals v naught times t plus 1/2 at squared, right? And the position at any time depends only on the time. It doesn't depend on the position. Okay, that's where it gets fucked. So how do we transfer momentum in a fluid? Okay, so if we allowed changes in the density, sure, you could increase the mass, right? In a local area.
Maybe you have to consider position, time, and velocity.
So as we move away from the kinematics is the mathematics necessary to just describe the changes. Now we're really beginning to think about the physics. The physics being what are the reasons for the change? We have to think about sources and sinks. Where does momentum come from and where does it go? Okay. Let's write that, write this version that we saw. Can I get rid of this? Let's write that version that we saw before. This is the integral formalism, and we'll move towards the derivative afterwards. Okay, so we're gonna still think about our control volume, some jelly bean shape or whatever shape you want to come up with in your head. And we're gonna say the rate of change of the integral over a volume of the density times the velocity. And I'm gonna do a really bad job here, so find this in your book if you want the exact letters, because I'm gonna drop X and T's left and right, okay? And we take this over the volume, right? So how do I generate momentum? I think you're describing like the fluid actually changing, which is not the wrong way to think about it, right? Like you're really thinking about like how is the fluid moving, but like why? What caused the fluid to move? A force, very good. Okay, so what are our forces? Do we have infinite forces that we can play with? Is the nuclear force at play here? No, hopefully not. Otherwise, you're dealing with a really, really bad time in fluids class. So let's be straightforward. What would be the most simple force we can use? Gravity. So your claim, Kevin, who just proposed this for the first time in the 600 BC, is that I can get fluid to move by changing how tall it is? Have we ever seen this happen before? Where? A mountain, it rolls downhill, right? So you can get velocity into the fluid by raising it up, right? And then it flows back down. And then you raise it up and it flows back down. Okay, waterfalls. We go and chase them. So let's do the first one. How does that work on the fluid itself? Well, you have some volume, and there's mass. There's gap. So the first term is a combination of those three. Easy breezy, right? Okay. Anything else? Any other way to do it? What? Well, that's gonna be in here. This,
Oh, because the gravity.
okay, so gravity can be a vector. So this is all of gravity. We just did all of gravity. That was good, right?
Maybe a time component.
Well, so I haven't written in there, but rho depends on x and t, and g depends on x and t, so don't worry about it. Gravity's done. We need a new force. Is there any other way to move fluids? What do you think? Pushing, pressures, I like these words, right? This is reminding me of like doing something to it. And I really like the word pushing, because that has an intuitive sense for me. Right? Pressure, I think, is something that I measure. Maybe for me personally, I'm having a hard time understanding like what causes the pressures. So if I think about, oh, what about, when I'm in the pool and I want to move water, what do?
Push it.
You push it, right? You literally can take the fluid, you can fucking do that, right? And then it goes up and it goes back down again. So I've created motion from the flailing of my arms. So now I'm thinking to myself, okay, wait, so now how did I work on that thing? So I touched the surface of it. So if there's some control volume, its force is acting on an area. Okay, that's where the pressure is. Okay, I'm getting it now, right? So let's write that down. That's gonna be written like this. This is gonna be on the area, the surface area of the object. And it's gonna be all my surface forces, which I'm gonna write with a little n. And this is the only one that I'm actually gonna put everything that goes in here. And because the direction of the forces really matter. Okay. So this thing here is gravity. And this F is surface forces. So I gave you the pool one. What's another example of a surface force?
Is that just the opposite direction?
Well, so if I'm acting on, right, so let's say this is the fluid, I push it like that. That's in the direction of the surface, at least in some regards. And you're saying it's going down like this. Yeah, that could certainly be a force, right? We'll see. We're gonna break that term apart. So there's body forces. That's the left term. What is acting on the whole body, the volume, and the surface forces. On the right-hand side, what is acting on the surface? And how are those two things, these two forces, communicated into the fluid? When I say communicated, I really mean that in the sense of like, if I make a change at the surface, how far down does that change go? The whole thing is in contact. So we saw one example of a body force. Is there any other body forces? One that I haven't written today? Is this a force or are either of those forces? Think about forces. We only have 4 forces, right? We eliminated gravity. Excuse me?
The strong, weak, and then.
Strong, weak. Electromagnetism, right? So we could, of course, if we wanted to, we could think about this fluid and we can say, oh, what's the charge distribution there? What is a very good source of charge inside of a fluid? I know this doesn't happen very often, but imagine if there was a lightning storm. Where do you not go? Water, yeah, water, bad idea, right? And what is it that's scary about being in the water? Are there free electrons in there, or is it salts and other stuff? There's dissolved salts, yeah. And also, what does water look like? You ever seen this one before? Mickey Mouse style, right? Or maybe I did it wrong, Mickey Mouse, but it's very polar, right? So if you're taking your kinematic, you have this connection between the 3, and there's a large dipole moment that's set up. Right? It's really good at conducting electricity. So you could imagine, let's say we subject the fluid to some form of a magnet or some electrical field, you could change the momentum. Right? You could accelerate the fluid by taking advantage of the natural dipole in the fluids. So you don't even have to have charge in the fluid. You don't have to have free electrons to get it to move because there's polarity. Now in practice, we won't do this, and I wrote the word gravity for a reason. That's the primary. But if you wanted to work in the field of, say, coronas, which are the hot atmospheres of stars, or if you wanted to think about plasmas, that's when you start adding in these extra terms.
Is that for all fluids? If they're all behave polarly, like, I'm just imagining like water, but I like, for example, if I have a giant pool of honey, they conduct lightning the same way as water.
Yeah. So that's really good. That's a really good question. Because, you know, one of the things we think about here is honey, we talked about earlier, you know, we have these conditions on what makes it a fluid. And we said that we need some distance between the molecules to be not so large that, you know, they don't travel very far without bouncing into one another. But we really never talked about the shape of the molecules, right? So for example, we thought about them just as billiard balls smacking into each other. But what's interesting and what's sticky about honey is the fact that those molecules have electromagnetic interactions with one another, right? There's forces that are drawing them to each other because they're not balls. What is it that makes honey?
Pollen.
Yeah, originally, but not at the sale of honey. Why honey so yummy? Sugar. What's sugar? What's the technical term for yummy? What?
Sucrose.
Yeah, sucrose, glucose, fructose, right? Those are all the names of sugars, and those are. Do we know the chemical? Yeah. So you can look up the chemical composition, right? The carbon groups, right? So depending on how you orient that carbon group, they might be longer chains or they might be smaller chains. And what we mean by that is instead of just having a single sugar bouncing around, you'll have complex sugar chains, right? So you'll have a bunch of them, and maybe they're all twisted around each other and they're all wrapped around each other, and they might still behave at large like a fluid, but you're absolutely right. They may no longer be either, maybe they're very polar, they're very easy to sort of align or misalign, or they're so complex that they lose all polarity. So you may have seen something called a ferrofluid. Right? A ferrofluid is something with iron filings inside the fluid, such that when you subject it to a magnetic field, then it is fully dominated by the body forces, right? And the magnetic filings align themselves directly. Right? Now, of course, they're suspended in a water solution, but you can imagine that with other objects. Is that kind of your answer, or is that too much of a tirade?
Yeah, I get it.
There's a wide variety, what I was trying to say. Helium is a great example of a superfluid. So when you cool down a fluid, right, helium is a great structure. Ball, spherical ball. Doesn't like to do chemistry with anyone. Hates participating in any chemistry, right? And in that particular circumstance, the shape there is just, you know, me and my electrons living my best life, right? And then it achieves really cool things like basically loses its viscosity. And it can do incredible things like climb out of the container that it's in, which most fluids can. Okay. What is it? What does it mean conservative body force? I'm not talking about how you voted. Yeah, what do you mean by that?
Be able to check it in another frame.
Sorry, so again, check it in another frame.
Yeah, like. Gravity exists already, but then you see how it works within this example.
Okay, yeah. I think you're coming at it from a kinematics point of view. And that's certainly not the wrong way to say it, but there's an easier way to say it. And we usually say that something is half independent if it's conservative. So what I mean by that is, let's start here, A and B. And this is height. Okay? So if I go from here to here, or if I go like this, okay? I will have to spend the same amount of energy. Right? And similarly, if I go backwards in either of those two paths, I will only get out the difference in h. So that's path independent, right? Which makes it conservative. If the integral is path independent. If the integral is path dependent, then it's not. So what would that be an example of? Path or path dependent. Yes, it does. Thinking of non-conservative forces here. Everyone's favorite non-conservative force. It's not really a force. So friction in this path A to B, the squiggly one, is more bends and turns. So I might spend more energy overcoming friction in this path than I would in this one. And therefore, by definition, it's not. That's fair?
Yes, it's conservative when it's absent.
Yeah, so in the absence of friction, they'll be conservative. And of course, we'll make statements like absent, but even just like, really low can sometimes work. Or since we just wait for it. It's mostly incompressible, like 99% incompressible. There's barely any friction. That's good, All right. The surface forces, that's the right-hand side. These are acting through direct action, right? They're happening on the surface itself. We talked about a couple different examples, maybe pressing, talked about slapping the top of the fluid. And so they have to go in the direction of the force, right? And they have to act on the face of the object. So this is why we need tensors. This is your face for the rest of the so we can write a couple different things here. We can say, by the way, that the conservative body forces here, G. So let's just finish this really quickly. This is G equals minus del. I don't know, you're sick and tired of this, but you didn't see this formalism before. So that's the gradient of the potential function, and then this is the force potential. And the only reason that I write it here sort of like separately is because we can think of that in terms of any force. So we're mostly going to do gravity in this class, but let's say you have gravity on a rotating body, like the Earth, right? Where, for example, gravity is moderated by how close you are to the equator. So you may or may not have ever experienced this, or you've certainly never noticed it. But as you move up and down on the surface, gravity changes. And as you move closer to the equator, gravity changes. Where is gravity the heaviest? That's, I know, a bad way of saying it, but forgive me. The poles, right? The poles, you are not helped out by what? Yeah, this is the right word. We call that getting flung off, right? So that's the centripetal acceleration, or the fact that you think that you're being thrown out, right? It's a fictitious force that comes from the fact that the reference frame is rotating. Okay, so you'll have the force potential, which is modified. It can be gravity, it can have electromagnetic forces, it can have centripetal accelerations, and that'll all be inside of G. Okay. So let's see. Ready to go sleep. Um. Okay, what are you gonna do right now? Doesn't matter. Uh, let's let's start here. Start back. Um. We'll delete this. One intermediate step, and we're gonna collect all the terms, and we're gonna see how it actually simplifies way down. Okay. So the first piece is using the Reynolds transport theorem. Remember that? The Reynolds transport theorem was saying that this piece here, the total time derivative of some quantity inside of a volume is due to unsteady and the advective part in that volume. Notice that's not what we said here, right? This is literally just doing the bookkeeping. On the left-hand side here, this is accounting for the gravity forces or body forces and surface forces. So on the left-hand side now, we can clarify this statement by saying something like, we take the derivative in, this is over a volume, it's dt of that thing, rho u, right? All over dt. Plus, now you need the area one. So this is the area. And this one's fun. So it's going to be rho u times u dot n. Okay. I should be a little more careful with this. I'm losing the plot. Yeah. So you had your unsteady term and your advective term. Okay. And this here is going to dot into each other. That's going to lose the direction. The direction's coming from the fluid motion. Okay, and that's just going to be what we had above. So G V plus the integral of any surface forces F. Yeah. Okay, so that's not so bad, right? Have you ever used Gauss's theorem? Yeah, so you know that we can go between surface integrals and volumes using Gauss's theorem. And so we can take this integral formalism and we can take this term right here, actually. Here's an area. Let's turn that into a volume integral. So let's turn that into a volume integral times, or sorry, of the divergence of rho mu u. Okay. And similarly here, I want to get rid of this one. So I am going to turn that into a volume integral of d dx of a quantity called Tij dx. Oh, there, D. And yes, I haven't defined Tij. Okay. But that's really nice because then all my integrals are in V, right? So now I'm just keeping track of everything that's in the volume. Do you have any problems yet? And then you don't like. Another way I could write this if we want. Could write it okay. Okay, so these are all over a volume. So let's put them all on the same side. So now I'm going to subtract these two, put them on the same side, have the whole thing. So this thing's gonna be some stuff equals 0, right? Is that true? So this is saying for some control volume, some jelly bean, all of the changes that happen inside here with respect to being unsteady, with respect to convection, they're due, they're due only to the body forces and surface forces. And so therefore, the stuff in there, right, must be integral of what is 0? Is that a weird thing to think about? What is the integral of? If the integral of a thing is equal to 0, that must mean that thing is what? Exactly, right? So the only way that that could possibly be true is if at every single point inside the volume, it's also true. Right? Kind of this cool property of the integral. Because you can't get it to be 0 for an arbitrary volume if there's any non-zero inside. Because then it could just change the size of the volume and make it not true. Does that make sense? So in fact, all of the stuff that I had trapped inside that volume integral, I now get to take out and set it. Right? So this stuff in here was 0. And so therefore I can equate. I can set the left-hand side and the right-hand side back equal to each other. So let's do that here. Okay. And I'm going to write this very simply. Okay. Now I said the word simply, that does not mean easy. Okay, because this is going to torment you for the semester. ddt of the quantity rho u. Now where did that come from?
That's the.
What?
What is it, what'd you write?
Why do you hate me?
It's visible.
Oh shit, am I doing it in the bad spots? Okay, let's do it over here. I'll do it over here. Is it better over here? So d dt of rho ui. Where does that come from? That's the first one. That's the unsteady term, right? Good. So what's the next term? Well, I didn't write it in the parentheses, but you should be able to read it. Excuse me?
Or we stay on higher.
Now we'll have J too. So when we have a repeated index, we sum over the repeated index, and J gives us the direction. Yes, maybe I should be a little more specific here. Let's make this one J so we match. What's the next term? Yes, that's correct. It's ddx of, what's that? You're going all the way to the end, right? So we have this term, this term, this term, and this term. So what's the next term?
Oh.
What? ddx what?
Oh,
No, ddx what?
I.
Good. Rho u
Stuff
I.
Use of it.
Correct. There we go. And what's that mean? Who the fuck knows, bro? You just showed us. Yes. But what did we mean when we said this part over here? We took this thing, this is the Reynolds transport theorem, and we broke it into two pieces. We call this piece the steady. And you remember that one really easily. That one's the easiest one to remember. This one is less intuitive, but it's the advective. So let's use that same terminology here. What are we doing? We're advecting.
Yeah.
What? Yeah, but what are we advecting? We're advecting the velocity. Good. Okay, so this is a weird one, right? This is where the complexity in fluid comes, because the property that you want is multiplied by the property that is doing the forcing, right? So advection, right, is the transport of velocity by velocity. It's fucked up, right? Okay. So this is your advective term of the momentum. And this is all going to be equal to. No. Good. And what's the gravity term? How do I write that? Good. No derivatives, right? Fucking suit. Now I'm going to be a little specific here. Let's do it this way. Do J. Okay, and then what?
Excellent.
Okay. Now what's TIG? TIJ. Yeah, right? So everything that's acting on the surface. And you may be lured into the false sense of hope and security that that only means stuff that's acting this on the surface. That's one version of the surface force, but this is just as correct. Pushing on, spreading across. Okay. And this one on the top can also be written as. This one on the top can also be written as. Correct. And how do I write that? I'm going to pull the row out just this way.
Right, over DP. Equal to, oh, you want to.
No, that's what I said. ddt the total derivative of rho uj. How could I pull rho out of there?
There's such a.
There is no j. No. J, remember, is the direction. So I'm writing in tensor notation because we are going to use tensors. So you will see me use the little arrow with the little vector symbol a lot less. And instead I'll be using this repeated index notation. And that is due all because this fucker right here. Okay? This is our stress strain tensor. Remember we talked about the way that parcels can deform? And we talked about the mathematics under which those deformations can occur. Now we're going to use them. Right? So let's say I push the fluid in some way, or I stretch the fluid in some way. It's going to change the velocity in the fluid. Right? That's the name of the game. That's the nonlinearity of fluids. Simone?
What happens when you use about?
Where? This one?
Yeah.
That's part of the effective term.
Oh, the big D or big D.
Yeah, big D is these two. Right? If you recall, the big D means we have this piece. And in particular, what it, the way that we should write this is something like this. Big D of something is equal to ddt plus rho, oh, sorry, hold on. Plus that same thing. Oops. Right? How much of that thing is going in the x direction? How much of that thing is going in the y direction? How much of that thing is going in the z direction? So this is asking the question, not only how is the momentum changing in time, but how much momentum is flowing in x? How much momentum is flowing in y? And how much momentum is flowing in z? And here's where it really fucks you, okay? Because that makes perfect sense. You're totally okay with that. You're ready to like continue on with the next class. Because you're thinking in your head, how much x momentum is flowing in x? Huh, that makes sense, right? But that's not what this says. This also includes how much y momentum is flowing in the direction x. How much z momentum is being transported by x. And of course, every other permutation. And that's why we need tensors, because there's 9 terms here. There's x in the direction of x. There's y in the direction of x. There's z in the direction of x, and every permutation on your box. Okay? This is sometimes called Cauchy's equation of motion. That's, you know, I don't know if you care, but we'll come back to it. We'll see it a lot. It's going to be really important that you feel that you can describe each term and that you know what they mean and you have an intuitive sense for where they come from. Okay. So now we're going to get sort of away from just the math, and we'll talk about how we use this in practice, and then we'll come back to the math at the end. So we need something called a constitutive relationship. So for example, we talked in some detail about rotation tensors and stress tensors, right? Strain tensors, that was the S and the R. And now we need to be able to connect them. Okay, so what we're really looking for is the relationship between stress and deformation. How does the parcel change, right? That's the result. And stress coming from the forces, how do we cause forces to change the shape of the parcel? See how these two words are different? I kind of use them interchangeably. I know that when we're talking about it, sometimes we slip up, but they're two different things. Stress is a force-based phenomenon. Deformation is the result. Okay. Okay. So the very first thing we need is T. So that is the same T. So no coincidence. We have to define this thing T that I wrote on the board, and I wrote it Tij. The first thing that I'm going to tell you is that Tij is equal to Tj. Oh fuck. I got excited. Tji. Whew. Thank God. Right? Everyone know what that means? What? Three dimensions? Yeah. Well, that's from the three dimensions of the class. But what is it? What have I written? Ij is equal to Jn.
Is that saying that the stress is equal to the deformation?
Not yet. We're gonna head in that direction, but that's not what just this piece is. Just for a matrix. What does this mean? Any matrix. That's the transpose.
I didn't see.
Of symmetric or a symmetric tensor. So I11, I mean, obviously that's equal to, you know, the first one's equal to the first one. But what about or say T12? Then that's equal to 2, 1. Okay. And so I think what your point is that if you transpose the matrix, you still get it back. Right, but we would call that symmetric. So for example, let's start writing some of these pieces down. T, right? I have the 3 diagonal spots. And then these pieces up here must be these pieces down here. Right? Okay. So Tij in a static fluid can only have isotropic stresses from pressure. What does isotropic mean? That'd be isentropic.
Interesting.
Isotropic. Iso means
No change in volume.
that'd be isentropic. Yours was isovolumetric. Iso means same everywhere. Isometric just means the property is the same everywhere. So for an isometric fluid, we say that the stresses can only be normal. Because if there's a component, for example, of say a pressure to the side, and you see it from an angle, then you can decompose that into x and y stresses as opposed to just x stress, right? So in fact, we can start. We can do the diagonals. We have the diagonals; they're really nice. It's Ij is equal to minus p, and it's just the question of whether or not this is the Kronecker delta. You like that one? Kronecker delta? Come on, folks, you gotta love these ones. Gotta tense up, So what is the Kronecker delta? Anyone remember? What properties does it have? Take on 2 quantities. This is the Kronecker delta. This is where it comes to define. The Kronecker delta has 2 values, either 0 or 1. When is it 0? That's correct, when I is not equal to j. What's that?
And I is
And when it is equal to j, it's 1. So that allows us to put the diagonals on right away. So if I look at this, right, I say Tij, so T11 is here. Is it? 1, yeah, 1. And so then I get what in the first position? Negative p. Good, what about the second position? I just went to diagonal, sorry. Yeah, we don't know anything about the off diagonal. They're going to be more complicated. Okay? The pressure is along the diagonal. What does that mean? That means in my box, right, the pressures along the diagonals happen in the direction of the pressure. As opposed to, we're thinking about how does the velocity get transferred, say, along an edge. That's not happening in the direction of pressure, right? That would be something else that we did. a different type of strength, of course. Okay. I know, it's getting more mathy. Gonna keep getting more mathy. Practice math, that helps. Questions, comments, concerns? Okay. We should talk at some point about a check-in. I think maybe one more homework and then we do it next week. Okay. Cool.